So the purpose of today's lesson is to go over Monte Carlo simulation um, and to just sort of do one in R to sort of figure out how that should all work. Okay, so what do we use Monte Carlo simulation for? Monte Carlo simulation is used to model random, so used to model random behavior. So we need a programming language, and of course in our class we're going to use R. So we need R's built-in pseudo-random number generator. There's a reason why it's called pseudo-random, but we're not going to really worry about that. We're just going to assume they're random enough. Pseudo-random number generator. That produces, let's just talk about the random numbers for a second. It produces uniform 0-1 random numbers, and we need to assign those. So we need to assign those in some way. So assign those to our random variables. So we're going to need to convert our uniform 0-1 numbers to whatever our random variables are supposed to represent. So R's uniform 0-1 numbers, the way that you access these is to use, it looks like runif, but it's not. It's R, meaning random variate, and then unif is uniform, and then you basically give it an n, a number n, which where n represents the number of uniform 0-1. So the number of uniform 0-1 random variates. That's really what the R stands for. Random variates that you want. So if you want 1,000, ask it for 1,000. All right, we'll show this. So we will show this when we get to R. So I'm going to show you what happens when we get to R. I don't want to jump over to R and do something and then jump back over here. So we will show this when we when we get to R. All right. So before we get going, let's do. I shouldn't say before we get going. Let's use this example 9.1 of the book. And basically, what it said in the book is and it's not 5 days. It's going to be 7 days. So over the next 7 days of our vacation, each particular day has a 50% chance of rain. The question is, what is the probability that we get rain on 3 consecutive days? So that's the question that we're trying to answer. What is the probability that we get if each one of these 7 days, not 5, but 7 days, is forecast to be 50% rain? What's the probability that we get 3 consecutive days of rain? So that is the question. And what we're going to use is this idea of this Monte Carlo simulation in order to answer that question. So first step, as always, we want to transform our problem. So we're going to transform our problem. First step, what are our variables? So I'm going to let this capital X of t, we're going to let that be the state on day t. So the state on day t. And that's going to be either a 0 or 1, basically. So you can let it be either one. So we're going to let 0 be no rain. So no rain. So if the x of 1 is 0, then that means there was no rain on on that particular day. X of 1 equals 1, then there was rain on that day. Where t is or I'm sorry, is equal to. So t is equal to 1, 2, dot, 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 all the way to 7. So there's 7 days in this little thing that we're trying to figure out. So my assumptions, so we have to make some assumptions about the setup of this thing, and I'm going to let each one of these random variables, x1, x2, all the way to x7. So I have 7 random things that are going to occur, and I'm going to say they are independent. And so that means this probability. So the probability that x sub t is equal to 1 given x of t minus 1, x of t minus 2, dot, 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 x of t, yeah, just dot, 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 because it can go back in time as far as you want to. But what we're seeing is they're all independent. So we don't really care about that it's given those things, and really it's just equal to x of t equals 1 is equal to, and in this case it says 50%, so 0.5. So we have regardless of what happened the day before or 2 days before or whatever, the probability that a particular day x1 through x7 is going to be equal to 1 is equal to 5. So that's what this thing says. Any one of those days is going to have a 0.5 possibility of being a 1 or a 0. Okay. So how are we? Well, I guess we got to write an objective next. So our objective is to determine if let's see, we'll call it xt minus 1, xt minus 2. Oops, let me redo that one. X of t minus 2 is equal, or all of the, I guess all of these are equal to 1 for t equal to, let's see, if t is equal to 3, 2, and 1, right? So for t is equal to 3, 4, all the way up to 7. So if that occurs, then for a particular 7-day window, then you get a 1. Then you get it's true. So in other words, the probability, actually we're not going to talk about probability yet, but on that particular week, when we simulate this thing, we'll end up talking about probabilities. But for one particular week, if this is true, then that particular week had 3 consecutive days. And so another way to do exactly what I have written here is to do this little trick, right? So I'm going to take, here, let me write it like this. Let's say that y is a 1 or a 0. So y is does the week. So does the week have 3 consecutive rainy days? All right, and then so y is a 0 or 1, so it's a Bernoulli distribution with some p. I don't know what the p is. That's what the purpose of this simulation is going to be, is to figure out what that p is. But one way of figuring out if a particular week, so let's call this function of x. So this vector x, and so these are random variates that come out of these random variables, x1, x2, x3. So let's set x equal to all of the days. So whatever happened on x1, x2, all the way to x7. So if I have this vector of values, 1s and 0s, then what I'm going to do is I'm going to let y equal to, here, let's get rid of this. So I'm going to let y equal to 0 or 1, 0 or 1. And the way that it's equal to 1 is if x1 times x2 times x3 plus x1, not 1. So again, this is a sort of a little trick here. Because we're dealing with zeros and ones, we can do something like this. So I don't have to use Boolean logic in order to do this. I can use this multiplication. So x3 times x4 times x5 plus x4 times x5 times x6. And then the last one, you can sort of see the pattern here. So I'm putting all of the ones that can be right beside each other together. So x1 through x3, x1 through x3, x2 through x4, 3 through 5, 4 and 6, 5 through 7. So if any of those is greater than 0, so in other words, there were 3 of those in a row that have 1s in them, then that whole thing's going to be 1. And then I'm going to be adding, so suppose that those were the only 3 that had 3 1s. The rest of them would be 0s, and when we get a 1. If I had all of them 1s, so in other words, there was rain every single day, then I'd have 1 here, a 1 here. So I'd have 5 of them. But really, all I care about is if this number is greater than or equal to 1, then I want to pass out a 1 out of this function. 0 otherwise. So I don't want to rewrite that entire thing. That's why I put otherwise on there. Okay, so that'll be my function that I use in order to figure out if I had 3 days consecutively once I start simulating this thing. Okay, how are we going to solve it? So the solution. So we're going to use Monte Carlo Simulation. So the way that we're going to do that is create 7 random variables, x1 through x7, and assign them a 0 or a 1 depending on the sort of the random numbers that are generated. Depending on random numbers that are generated. Okay, so hopefully your question is, well, how do I take a uniform 0, 1 number and how do I turn that into? So that's a good question. So let's go ahead and write that one down. So how do we take a uniform 0, 1 number, right? 0.5, 0.32, 0.78, I mean, all these uniform 0, 1 numbers, and turn them into a 0 or a 1, so 2 discrete numbers. Hopefully that's a good question, or one that you might be answering yourself. Suppose like we had a coin flip. So we're going to let x be, and that's basically what this is a coin flip, right? Because it's 0.5 probability. So we'll let x be head. Let's see. X is defined as getting a head on a coin flip. Okay. X is a Bernoulli. And in this case, we know probability of success is 0.5 if we assume that we have an unbiased coin. And then how is X distributed? Well, here, let's draw our little distribution here. So X is here, P of X. So we got 0 and 1 is the support for this distribution. And we have 0.5 and 0.5. All right, so what is f of x? What is the probability x is less than or equal to? Well, that's 0.5, and that one's a 1. So let's see how this cumulative distribution function can be used in order to create this 0 or 1. So if I were to graph this thing out, I think it's easy to see the graph. So let's put on, yeah, that'll be fine. And see, we'll make this guy be 0, and this one be 1. And then in this case, we got 0.5 is here, and then 1 is up here. And so if I were going to graph the CDF, it would look like this little step function. It comes in at 0. Before 0, it's going to be at 0, and then when it gets to 0, it's going to shoot up to 0.5. And then it's going to stay at 0.5 until we get to 1, and it's going to shoot up here to 1, and it's going to be 1 for the rest of the eternity. It's going to stay at 1. So how can we use, so if you notice, these, I can put in uniform 0, 1 numbers on this side, and I can shoot over in this direction, and I can land here and then shoot down and be at 1. So if my uniform 0, 1 number, is between 0.5 and 1, somewhere in this area, then we can call that a 1. If it's between 0 and 0.5, then we can call that a 0. So what are we doing here mathematically? If I'm coming in from the y-axis, if you will, if you would just think of this, or the f-axis, the function axis, and then get values that are on my x-axis, right? So that's x, and maybe this is f of x. So what is that called? It's using the inverse, right? So it's the same thing as an inverse function. So what we want to do is we want to find the inverse of f of x. And I don't think I've written out what f of x is. So in this particular case, f of x is equal to, we could do it just by the graph here. We could just sort of look and see. Obviously, if if u is between 0 and 0.5, then we want x to be 0. If u is between 0 and 0.5 and 1, then we want x to be 1. So that's a pretty easy way of looking at it. But let's real quickly just write out what f of x is. So f of x is 0 if x is less than 0. X is equal to 1/2 when x is between, let's see, 0 is less than or equal to x is less than 1. And then we're at 1 when x is greater than or equal to 1. So the inverse function of this one, so inverse would be, we put in our u's, is just to, I'm going to be 0 or 1 if u is between, so what is it, 0 and 0.5. We can give it a 0.5, and then I'm going to be 1 if u is between 0.5 and 1. So this is the inverse function, and u's are going in, and what's happening is x's are coming out. So x is equal to that. Just to make sure we get it, or we understand sort of what's going on here, I'm going to now do the same thing for a dice roll, because a dice roll is a little bit more difficult. It's not difficult at all, but it's a little bit harder than just a Bernoulli trial. So I'm going to redefine x. I'm going to redefine our random variable x as a single die roll. So a single die roll. And obviously, it would be the number of dots that's on the face of the die, blah, blah, blah. And so we know x is distributed, if it's a fair die, and that's what we're going to assume, just like we assumed a fair coin. So x, p of x, it might be smart if we didn't assume a fair die. Maybe we have one number that lands more than another, but maybe we can see something a little bit different. Yeah, let's do that. Let's create ourselves an unfair die. 3, 4, 5, and 6. So that's the support for this distribution. And let's say that it lands on 2 half the time. A little crazy. And then what does that mean about the rest? We'll say 2 or 1/6 of the time that it does this, 1/6 of the time that it does that. So that's 3, 4, 5. I got 1/6 left with 3 numbers, so I can be, I believe, let's see, divided by 3, 6, 18. So 1/18. Obviously, this has to add up to 1. We would be no good if it didn't. So let's just make sure 3/18 is 1/6, 2/6, 3/6, 6/6. Okay, so I think this works. So let's find out what happens now. So so let's get the CDF, f of x, and which, let me write the probability statement for that. So the probability that your random variable is less than or equal to whatever this small x is, and this is your lowercase x that goes into this number here. And so that is also the lowercase x. So that would be 1/6, because it would be less than or equal to 1. And so, and then we're going to accumulate probability. So we'd be 4/6 there. We would be, let's see, 1/6 would be 5/6. So most of the probability is going to occur between 1 and 3. And then we have, so 1/18. So what is that? 18, 15, so that'd be 16/18, 17/18, and 1. All right, good. It added up to 1. Let's insert our diagram here, or our chart. Let's see, so maybe that many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is 12 good enough? I don't know. We'll see. All right, so let's see how this little CDF is going to work. But we do know that's 1, 2, 3, 4, 5, 6. And then let's break it up into sixths. Probably what I should have just done from the beginning. So we'll let this be 1/6, 2/6, 3/6, 4, 5, and 6. So this would be 1/6, and so on and so forth. And then this last little piece here is going to have 3. This last little edge here is going to have 3 numbers that are fighting over that last little bit of probability. But that's okay. So what would that look like? So the first one is gonna, so we're gonna be at 0. This would be 1, 2, 3, 4, 5, and 6. And then this one would come up to 1/6. And then because 2 is such a heavy hitter here, it's gonna go up by 3 numbers all the way up to 4/6. So it's gonna go up to here. Right, and then it's going to come over and it's going to go up another 1/6. Right, and what's going to happen at 4 is it's only going to go up just a little bit, maybe 1/3 of this little box here. And then I want to try to get this as close as possible. And then 1/3 here, and then 1/3 there. No. Maybe that's those 2 suckers out of the way. So maybe that's 1/3, and maybe it goes up 1/3 here, and then it goes all the way to the top. Okay, so this one's going to come over, and then go up another 1/3, and come over and go up another 1/3. All right. So remember what we just said previously for the Bernoulli trials, right? So we're putting these uniform 0, 1 numbers in this fashion, and what's going to happen is they're going to accumulate down at the bottom. And so as you can see, because the height of this one is so large, it's basically 1/2 of the entire amount, right? So so any number between 1/6 and 4/6 is going to accumulate a 2. So you can see we're going to get a lot more 2s. If the numbers that are coming in here are uniformly dispersed between 0 and 1, then we would expect about half of the numbers to show up down here underneath 2. And then we'd expect about 1/6 of the numbers to be here. Why? Because of this height of this thing right here. We expect about 1/6 of the time that you'd be between 1/6 or 0 and 1/6, and so on and so forth. And so we would start accumulating the correct number of numbers, if you will. So what would that look like if I was going to write out, here, I won't write the CDF out again. I'll write the inverse CDF. So let's do that. Let's just write out the inverse CDF just so you can see, hopefully you get what's going on here and why it's doing what it's doing. But if I got a number between, so if my uniform number was between 0, U and, let's see, let's put, in this case, 1/6. And we can put 1/6 on the other side. So I'll take off that equal sign. I'll take off the equal sign on the right-hand side. So if that's the case, then I'm going to throw a 1. If I'm between, if I'm between 1/6 and 2/6, is it 2/6? No, 1/6 and 4/6. Then I'm going to let a 2 come out. If I'm between 4/6 and 5/6, then that's going to be a 3. And if I'm between, let's see, 16, so 5/6 and 16/6, no, 16/18, I should say, then I'm going to let a 4. 5 will be 16/18 and 17/18. And then 6 will be if U is greater than 17/18 or equal to. Okay, so that's how you would do a dice roll if your die was very unfair. So this would be if, and so on and so forth. Okay, and we could model that using R and uniform 0-1 numbers. That would be a very straightforward thing to do. Okay, so let's get back to our problem. So get back to our problem. So we're going to use the one that we just talked about. So I'm going to create 7 random variables, x1, x2, x7, that have a 0 or a 1. And then I'm going to let y be a 0 or a 1 based on that equation based on our equation here. We'll call this equation 1. So based on equation 1. And then we'll run a whole bunch of them. Let's run 100,000 of these things. So what we're doing is we're accumulating like, so we only have 1 week to actually do this, but what we want to do is we want to accumulate experience. Like, what would have happened if this were 7 days and you had a 50% chance of this occurring? Each day of it raining. So what would that look like if we did that? So I want to accumulate 100,000 simulations of these weeks, if you will, and then let's just look at the distribution. So we could look at the distribution. We could look at the mean. So what would y bar be? Let's think about that for a second. Y bar would be so that would be the average. So what we're doing is summing all the 0s and 1s up top, but all of the 1s are basically the only thing that's going to get added. And what does it mean to be a 1? So that would be the total weeks that had 3 consecutive days of rain. It's sort of what we defined as being the one above. And then what goes on the bottom is, all the weeks. So all weeks, or N, if you will, whatever our capital N is. So if capital N's 100,000, well then 100,000 would go in here on the bottom. So this would give us about, with the probability of getting, after looking at our experience of what happened over those 100,000 runs, this would be sort of the probability of getting 3 consecutive rainy days, approximately equal to that. It's not perfect, right? Because this is a random experiment, just like any random experiment. We expect this thing to be pretty close, especially if you're doing 100,000 experiment. But we could use statistics in order to figure out how close we are. Okay, with all that being said, let's go ahead and use R. So I'm going to stop sharing this and put the little R share in. Okay, so the first thing that I think I said was we're going to just grab 100,000 or maybe 10,000. I don't know. It looks like runif. It's not runif. It's random variate of uniform distribution, and then it shows you what the. So you can put N. You could change the 0, 1. You could change it to whatever uniform distribution you're interested in. We're going to leave the min 0 and the max equal to 1. So we'll just do, I don't know, 100,000 of them, and then histogram X. Let's see what happens. Okay, so you can see down here that it gives you about a uniform numbers between, all these numbers are between 0 and 1, and so that's exactly what we'd expect. And the frequencies over here with the histogram, I didn't tell it to do it by distribution. I just give me the frequency. And if we have 100,000, then you'd probably expect however many of these bins that we have divided by 100,000. I'd expect about that many at the top, right? So you can see that it is distributed normally, or uniformly, I should say, throughout my axis. Okay, so now what we want to do is just create that function first. So create, I'll call it equation 1. And we know how we're going to distribute our, what the input is going to look like. So let's call it consecutive. Consecutive is equal to function, and I'm going to input in X. And I'm going to let Y equal to X1 times X2 times X3. X3 plus, and I'm going to go to another line just so it's very clear that I multiplied and added where I was supposed to. X2 times X3 times X4. I've found that if I put it on another line, it makes me a lot more comfortable that I did it what I was supposed to do. So X3 times 4 and 5. And this should align with what we've already talked about. Let's see, the next one is 5, and the last one is 5, 6, 5, 6, and 7. All right, so that's what Y is going to be equal to. And then the very last thing is I just want to return what happened, right? So we can just do an if statement here. So if Y is greater than or equal to 1, then we want to return, if you remember, we want to return 1 if it's greater than 1. So if any of those things are true, each one of them being 1, then I want to return a 1 if any of them are true. And then else, if none of them are true, then I want to return 0. So that should get what we're looking for. But just in case, I mean, every time you write a little function like this, you want to test it. So I'm going to let x, this little small x, equal to c of 1, 1, 1, 1, 1, 1, 1. And then I'm going to run it through consecutive. So consecutive x, should be a small X, so can enter. Oh, I couldn't find it because I didn't run it yet. Control enter, and we see this equal to 1. So that should make you feel comfortable, at least on that one. And now I'm going to take out all of the consecutive ones and see that it equals 0, and I'm going to put just one of them back in, and we see it's 1. Okay, so it looks like it works. I haven't tested every single possibility yet, but it looks like it works. So we're gonna drive on from there, and maybe we'll see something later on if it's not. But I think we're good. Rainy. So I'm gonna have this other function called rainy days, and it's gonna equal to, let's see, let's make it a function of p. Now, what would p be? It's our probability of getting a rainy day. So in other words, like maybe we do this later on in our sensitivity analysis is, well, how sensitive is this to the probability of any particular day being a rainy day? Obviously, it should be very, I don't know. I mean, I have to run it and see, but it seems like it should be very sensitive to that. Because if you only have a 10% chance of that happening, well, then that would be very unlikely that you get 3 days in a row. And if you're at 90%, then you'd probably be very likely that you would get it. So, I mean, we can run this later on. So I'm going to the first thing I'm going to do is let these uniform 0, 1 numbers. So run if, oops, I forgot my equal sign. So run if, you can say it like that if you want, R uniform, random variable uniform, and then I'm going to let it be 7 days. And then we can print U. And then I want capital X. I want the random variables to be, let's see, if U is less than P, all right, in this case, if it's 0.5, it would go in. So my uniform numbers, if they're less than P, I think if you did like this, it would be true or false. So if you multiply it by 1, then we should be good to go there. And then let's print X. Let's find out what happens. So let's run that and let's find out what happens. So let's go rainy days 0.5 and find out what happens. Right, so 0.3 was 1, was less than P was equal to 1. Is that what we said earlier? I mean, it doesn't matter which side you put it on. Let's see, but do I want that to be the probability of success? I want that to be the probability of failure. So the 0, so U minus P, maybe we make this, maybe we make this one, so how about great, less than, so if U or P is less than U, either one of those, so U is great, if U is greater than P, I want that to be a success. Yes, that's what I want. I believe that's how we talked about it earlier. So 0.87, 0.93, 0.77, 0.544. Now, what happens if 7, that to be my probability? Yeah, that's not working. Because the only one that's, I want it 70% of the time. Yeah, so let's turn this back into less than. All right, let's see if that works. So now we get 70%. All right, so that one's turned into a 0. Yeah, so this is what we want it to be. So it's rainy days, 0.7. So let's go back to 0.5. And make sure that we get what we want. 0.4. So if it's less than 0.5, then we're getting what we want. Okay, so that's good. I mean, there's a couple of different ways of doing this. I could have said that 0.5 is my problem. Instead of probability of success, that's probability of failure, and then worked it out the other way, but I don't like that at all. I like 0.5 being my probability of success. Now that we kind of know that this thing is working, I want to go ahead and get rid of, ooh, you know what we forgot to do was to say, to run it through y is equal to consecutive and return y. Let's do that. Make sure that it's doing what we think it should be doing. So I got 3 and I got a 1, and the 3 corresponded to those 3, which is correct. Okay, good. Let's do it again. We got a 1 again, and there we got 0. And it looks like consecutive is working. Looks like everything's working the way it should. So I'm going to get rid of my print statements. And now Control Enter. So now I don't know what happened, right? So I'm just taking it for what it's worth. I'm taking rainy days to work the way we intended to work, and that's why you do a little validation beforehand. Okay, so now we're gonna collect our information. So we're gonna let answer, it's just something that I like to do. I like to set it to equal to answer. We'll see what happens. We'll set n equal to maybe 100,000, because I think we said earlier that we're gonna do 100,000 of these, and then just simply roll through for I and 1 through n. We will get answer I will equal to rainy days again, rainy days of P, where we set P. All right, I believe we are sitting where we want to sit, and we want to do maybe mean of answer and then standard. All right, let's find out what happens. Control Enter. All right, so we've ran this thing, and like we said earlier, we're going to find the mean. So you find the mean, you get 3.36764, and with a standard deviation of 0.482. So it looks like a fine answer to me. 0.367 probably. I think the book said 40%, but they only did 100. I guess if you rounded this sucker up, you would get 40%. But we're going to keep our answer as 0.37. And we could do a confidence interval. We could do a couple things. Let's just say let's just look at 2 standard deviations away from the mean. So if I wanted to print that off, I'm going to do it up here. If I wanted to print something that looked like 2 standard deviations away from the mean, then we're going to use this cat function. What this cat function does is it lets us to put multiple strings in a row. I think it's concatenate or whatever cat means in our language. And then I'm going to put the mean of answer minus 2 times the standard deviation of answer. And let's see, so that would be a parenthesis, a number. Maybe I put a comma in between them. And then another number, so mean of answer minus 2 times the standard deviation of answer. So what we're doing now is we're just basically getting an interval and maybe a parenthesis at the end, and then I want to go to the next line. So you got to actually, in this cat function, you got to tell it that you want it to go to the next line as well. Oh, that doesn't look right at all. So, plus. And, so what did I do wrong here? We forgot to use, our one thing about the expected, or the x bar, is that you got to divide by the square root of n. Don't forget to do that, or you get some kind of crazy number. So we divide by the square root of n. What do we get there? So it should be centered on 0.3674, and then the standard deviation divided by the square root of n is going to give you, this one's wrong, obviously, because it's really negative and that doesn't make any sense at all. But this one is sort of centered on where we think it should be centered. All right, let's run a couple of them then. Let's run another one. Control Enter. Takes a second, and then it gives us another interval. So we think we're probably have the answer in this interval. So what the true answer is, we don't know what it is unless we did it found the theoretical distribution, and we could definitely do that, because this is not a, I don't think this is that difficult of a problem to find, but I think this simulation is one that kind of shows you how we would go about doing this work. All right, that's all I got. We will do another problem like this in class, so be prepared. And I will post all of this on the internet. I mean, on our web page. I'll post all of this information on the web page. All right.